Hello and welcome to this video on how you can make a sawtooth wave generator. We'll be going over how we can create this wave by charging and discharging a capacitor. A sawtooth wave can be described as a linear ramp and a steep drop-off. We'll go over how we can affect the shape of the wave and other design considerations. Let's take a look at the circuit. To create this sawtooth wave, we're going to use a square wave for the input. You can use a function generator or a 555 timer, a Schmitt trigger, something that can generate a positive and negative square wave input. We then have a coupling capacitor to couple the AC input wave into the base of the transistor. Next is a biasing resistor. Then we have a current setting resistor that connects from the power supply to the collector of the NPN transistor. The emitter is grounded in this configuration. The key to this sawtooth generator is the capacitor in the output. We're going to be charging and discharging this capacitor. Let's remove the capacitor for a moment to get an understanding of the fundamental behavior of the circuit. This transistor configuration is used like a switch. When the input signal turns the circuit on, the maximum amount of current flows from the collector to the emitter, but the voltage across the collector-emitter junction and the output voltage are approximately equal to zero. When the circuit is turned off, the minimum amount of current flows from the collector to the emitter, but there's a large voltage across the collector-emitter junction and the output. It's approximately equal to the supply voltage. Here's a look at the input and output when there's no capacitor connected to the output. The input signal is a plus and minus 2 volt peak-to-peak square wave. Notice that when the output is high, the input is negative. This is when the transistor is off. The output voltage is approximately equal to the collector-emitter junction voltage across the transistor, and it's approximately equal to the supply voltage. When the input signal is turned on or high, the transistor turns on, and the output voltage is approximately equal to zero. The output voltage follows the collector-emitter junction voltage. Let's add the capacitor back into the circuit and see how it behaves. Here's the output with a 0.01 microfarad capacitor plugged in parallel with the output. I used the persist feature of my oscilloscope to keep previous acquisitions on the screen, so we can see what it looks like with the square wave output with no capacitor and with the capacitor plugged in. Notice how the edge starts to round of the square wave. This is due to the capacitor charging up. The capacitor charges at a rate that's determined by the time constant, which is resistance times capacitance. And in our case, the resistance is the collector resistor, and the capacitor is the one that's selected in parallel with the output. The capacitor will fully charge in 5 time constants. So here, the capacitance is too small to create a sawtooth waveform. The next capacitor selected was a 0.1 microfarad capacitor, so it's 10 times larger. Notice how there's a slower charging rate, and the output amplitude decreases slightly. Notice how we weren't able to fully charge up the capacitor like in the 0.01 microfarad case, where we fully charge the capacitor to the maximum output voltage. The last capacitor I selected in this waveform was a 0.22 microfarad capacitor. Notice how the amplitude is about half of what it was for the fully charged capacitor, but we get a more linear signal. We're getting closer to the sawtooth waveform. When we create the sawtooth, we're approximating a linear ramp and a steep drop-off, but we have to select the right capacitor given our input square wave. Here is the 0.22 microfarad capacitor plugged in without all the other waveforms in the background. Now I'll plug in a 1 microfarad capacitor. Notice how the amplitude is decreased pretty severely, but we get a nice, approximately linear rise in a steep fall. This sawtooth wave has a 50% duty cycle, meaning it's on for half the time and it's off for the other. This is because we're using a 50% duty cycle input square wave as well. We can change the duty cycle by controlling when the transistor gets turned on. When the transistor is on, we force the output to go to 0. If we didn't force the output to 0, then we would discharge the capacitor at a rate determined by the time constant. This last clip is the input and output. The input is the pink wave, and it's a voltage measured at the base emitter junction. Thank you for watching this video on the Sawtooth wave generator. This is a good start, but there are a few improvements we can make to this circuit, and I'll be highlighting those in future videos. Stay tuned for more content, and let me know what you think in the comment section.